Okay, so if everyone's ready, I can go ahead and get started. So we finished last time talking about little groups at high symmetry K points in the Shubnikov space groups. And we saw how, at least for type 1 Shubnikov space groups, at high symmetry K points, what we found is that the eigenfunctions of the Schrodinger equation, so our Bloch eigenstates for our electrons, transform in irreducible representations of the little group at each K. And that those irreducible representations, we can get them by looking at the sewing matrices for the symmetries for any of our given band structures. And so what this means for type 1 groups what this means is if we plot out a band structure, it's a function of momentum and energy, we'll have some bands. Let's draw them like this. They'll do what they do. And so these, at this K point here, let's call it K0, let's call this point K1. These eigenstates here are degenerate because these two states transform in an irreducible representation of GK0, as do these states. And each of these, this state transforms in some representation of GK1. And we can label all of these degeneracies at the high symmetry K points by the irreducible or by an irreducible representation of the little group. And so the sizes of these representations tell us about band degeneracies that can't be split without breaking symmetries of the space group. That's for type 1 groups, where we didn't have to worry about any operations that reverse time. Once we have time reversing operations, so in type 2, 3, and 4 Shubnikov space groups, things get a little bit more complicated. So type 2 to 4 groups. Oh, that's a 6, not a 4. Well, in type 2 groups, our space group has the form a type 1 group union time reversal times a type 1 group. And there's two possibilities for the little group at each K point in this space group, in a type 2 group. Either we're at a K point that's equivalent to minus itself. So K is equivalent to minus K. These are called time reversal invariant momenta. Time reversal invariant momenta, which in the literature are often abbreviated trim points. We have that K is equivalent to minus K, mod or reciprocal lattice vector. And at these points, that means that time reversal symmetry is in the little group of that K point, because time reversal takes K to minus K. And so in this case, the little group M sub K is a type 2 Shubnikov space group. Otherwise, M sub K is a type 1 Shubnikov space group. So whether in a type 2 group, whether the little group of a given K point is type 1 or type 2 depends on if that K point is time reversal invariant. And it's a similar story in the type 3 and type 4 space groups. Similar in type 3 or 4. So in type 3, the little group of any K point is either a type 3 group or a type 1 group. And in a type 4 group, as you might guess, M sub k is either a type 3 group or type 4 group or type 1 group. Okay, so to understand the constraints that magnetic space group symmetries place on electronic bands in these space groups, we need to understand how to represent anti-unitary symmetries acting on our block states. So let's consider a time reversing operation. We'll denote it as GK times time reversal in the little group of some K point. So we saw last time how we can write down the sewing matrix for such an anti-unitary symmetry or time reversing symmetry. It acts as an anti-unitary operator on our Hilbert space of states. And by inserting a complete set of states, we can define a sewing matrix for this anti-unitary symmetry. And that sewing matrix was our B K of GK times time reversal. And as we remarked on at the end of last lecture, this sewing matrix is still a unitary matrix. So we need to do a little bit more work. The reason we need to do a little bit more work is because this sewing matrix is all well and good for telling us how the symmetry acts on our basis states. But when we take linear combinations of our states, our multiplier states, by a complex number, sorry, is everything okay with the audio and the video?
I think your camera was somehow shut off.
Oh, that's strange.
But you can continue. I don't
Okay.
think.
Okay. So we need to account for the fact that if we multiply our states by a complex number and then act with our anti-unitary symmetry, this is equal to acting first with our anti-unitary symmetry and multiplying by the complex conjugate of that complex number. And to account for this, we're going to introduce a shorthand operation which I'll write as script K. which represents the action of complex conjugation on scalars. And if we introduce this K, then we can represent our anti-unitary symmetry by sewing matrix times our complex conjugation operations, with the understanding that complex conjugation here acts on scalars that multiply our basis vectors. So now we have a set of matrices that represent the elements of the little group, where time orientation preserving operations are represented by unitary matrices, and time reversing operations are represented by anti-unitary operators, written as a product of a unitary times complex conjugation. So an object like this, a representation where we have both unitary and anti-unitary operations, is a little bit different from the standard linear representations that we usually are used to, and so we give them a different name. So a set of representation matrices with both unitary and anti-unitary operators is called a co-representation. And we'll sometimes abbreviate that co-rep. So when we're dealing with type 2, 3, and 4 magnetic groups, or Shubnikov space groups, when we talk about the representations of their little groups, we really need to be looking at co-representations and irreducible co-representations. So we can do a quick example of a type 3 group where we can see how all of this works. But maybe before we do that, does anybody have any questions? Okay, don't see any hands. So let's look at an example. We'll do two examples, one with a type 3 group and one with a type 4 group. So let's look at the type 3 magnetic space group P4 prime. So this has primitive tetragonal Bravais lattice and a fourfold rotation composed with time reversal symmetry. So we can write this as the type 1 group P2 with primitive group with twofold rotation symmetry, union C4Z times time reversal, multiplying all of the elements of the type 1 group P2. And if we want to write out the generators of this group explicitly, we have translation by lattice constant A in the x direction, translation by lattice constant A in the y direction, translation in the z direction, our operation C4Z times time reversal, C2Z, which is the twofold rotation we get when we square this, and then our 2 pi rotation E bar and our identity rotation E. So we can label some points in the Brillouin zone of this space group. They're the same points that we looked at the example of the type 1 group P4 that we considered last lecture. So if I plot out Kx, Ky, for simplicity, let's just fix Kz equal to 0. So we have the gamma point with coordinates 0, 0, 0, our x point coordinates 1/2, 0, 0, M, coordinates 1/2, 1/2, 0, and Y. Zero, 1/2, 0. So we can ask about the little groups of each of these points. So if we look at the gamma point, well, the gamma point has coordinates 0, 0, 0. It's a time reversal invariant momenta. 0 is equal to -0. And it's invariant under any rotations. And that means that the little group of the gamma point is just going to be the entire space group. So this is a type 3 group. If we look at the M point, we have similar analysis to what we did last time. If we look at what happens to the M point when we do our fourfold rotation times time reversal, well, a fourfold rotation takes this point 1/2, 1/2, 0 over to this point, minus 1/2, 1/2, 0. And then time reversal takes it down here. But this point down here differs from M by one of our reciprocal lattice vectors. We just translate by 1 in the y direction. So this M point is invariant under C4 times time reversal. And that means that the little group of the M point contains all of our rotations as well. It's also a type 3 group. Now, what about the X and the Y points? Well, C4, as we saw last time, takes the X point to the Y point. Time reversal brings it to minus the Y point. That's still not equivalent to the X point. So the little groups of X and Y are both given by P2. They contain a twofold rotation still, but they don't contain our anti-unitary operation. So these are type 1 groups. And so we can use the tools on the Bilbao crystallographic server to look up all of the irreducible co-representations for these points. And I'll walk through that for, let's say, the M point, well, the gamma point. We've already seen what the irreducible co-representations for type 1 groups look like. So let's see what happens at the M point. So to do that, we'll hop over here to the Bilbao website. I'll zoom in so that everybody can see. So we'll go over to magnetic point and space groups again. And now we want co-representations of the magnetic groups. So we'll choose our magnetic space group. We want to look at the space group P4 prime. So we first go to symbol P4. And now we see the type 3 group P4 prime. So we'll click on it. Now we can choose our K point, and we'll choose the gamma point. And we get a nice table with the labels of the irreducible co-representations. There's 3 of them now. And the representation matrices for each of the symmetry operations. We see here that this gamma 1 co-representation has dimension 1. Its representation matrices are just numbers. The other 2 co-representations have dimension 2. So the way to read this, we can see first, if we look at our E bar element represented by superscript D1 on the Bilbao server, these first 2 co-representations have E bar represented by plus the identity. So these are applicable to spin 0 particles or fermions without spin orbit coupling. And we have 1 co-representation with E bar represented by minus the identity. It's applicable to spin orbit coupled systems. Here we have all the matrix representations for the unitary operations, and everything in red with a prime is the sewing matrix for an anti-unitary operation. And it's implicit here that this is just the unitary part B of the representation matrix. When we want to use these to compute how these symmetry operations act on on eigenstates, we need to remember that there's also this implicit complex conjugation operation.
Sorry.
Yes.
Can I ask a naive question?
Yes.
How are these matrices generated?
Good. So everything's sort of generated in steps. So the building block of everything is the representations of the type 1 groups. And these are ordinary group representations. So to generate those, what you can do is there are a few ways that you can do it. Maybe the easiest way to do it is to take representations that we know for the full rotation group, so our angular momentum representations, and just start systematically leaving out operations that aren't in the space group. And so this lets us generate all of the representations, or all of the irreducible representations of the magnetic, or of the type 1 space groups. There's other ways that you can build things up from the representations of the translation group, but at any rate, suppose we have the type 1 group representations. Then what we can do is ask about how we can add our anti-unitary operation to these and see if there's some way that we can find an anti-unitary matrix that sits inside the representations we already have. And there is an invariant that we can compute for every group. It's called the Frobenius-Schur indicator. And it's the sum of the traces of the squares of all of the representation matrices. But it has the nice property that if it's equal to +1, then it's possible to find a representation for the anti-unitary operation. And if it's not equal to +1, then the anti-unitary actually relates to different type 1 representations that sort of pair up under time reversal. So you can think of, if you have a spin-up electron, you know how a spin-up electron behaves under rotations about the axis of spin, but time reversal takes spin up to spin down. So we can't just add time reversal as something we represent on our spin-up electron. We have to pair it with the Hilbert space for a spin-down electron. And it's a similar process for generating these magnetic space group representations. Does that help answer your question?
Yeah.
Okay. And actually, let me go back to the website. We can see this process reflected a little bit in the names of the representations. So you see how some of these representations have a name that looks like two names just stuck together, like gamma 2, or gamma 3 bar, gamma 4 bar. And what this is telling you is that our anti-unitary operation pairs together two type 1 representations, in this case, gamma 2 and gamma 2, or gamma 3 bar and gamma 4 bar. So good. So let's look at a type 4 example next. And in that example, we'll see something that we can do that's interesting, and how type 4 magnetic space groups allow for some band structures that we can't necessarily get in non-magnetic or type 1 space groups.
Or just to let you know, your iPad screen is not.
Okay. There it goes. So let's look at type 4 space group, very simple type 4 space group with symbol P sub C1. So if we dissect the symbol a little bit, the 1 here means that there's no rotation or reflection symmetries other than the identity. And the P sub C means that this group has an anti-unitary operation that is a composition of a half lattice translation along the z-axis, which is the c direction, times time reversal. So this group just has some Bravais lattice vectors that I'll denote along the XYZ axes just for simplicity. And it has our anti-unitary time reversal composed with a lattice translation and our identity and E bar. Now let's take a look at this anti-unitary operation, C/2 translation times time reversal. So this operation, if I write it out in terms of site symbols, looks like this. And let's see what happens when I square this operation. So if I square this operation, well, time reversal squared gives me E bar. And my translation squared gives me my Bravais lattice translation. And I'll write this as the product of two operations, just E bar with no translation and my Bravais lattice translation. So I know how this has to be represented. This operation, well, it's in the little group of every k point because translations leave k invariant and E bar leaves k invariant. And I know how this thing has to be represented on Hilbert space. The sewing matrix for this operation has to be for spin orbit coupled fermions, -1 from the representation of E bar, and then a block phase, e to the I k dot, write it as k3 times 2 pi, where k3 is my third coordinate of my k vector in reduced coordinates. So at k3 equals 0 in that whole plane, this thing is equal to -1. When k3 equals a half, so halfway across the boundary of the Brillouin zone, this is equal to -1 times -1, which is equal to +1. So let's look at two k points. Let's look at the gamma point, k equals 0, 0, 0, and the z point, 0, 0, 1/2. The little gamma and z are both time reversal invariant momenta because they're at either, well, gamma always is, and z is at the boundary of the Brillouin zone. It's equal to -z. So our anti-unitary operation is in the little group of both of these points. At the gamma point, that means we have an anti-unitary operation in the little group that squares, whose representation has to square to minus the identity. And whenever we have an anti-unitary that squares to minus the identity, Kramer's theorem tells us that we have to have a twofold degeneracy. At the z point, we still have an anti-unitary symmetry, but it squares to +1. And that means we don't have any Kramer's degeneracy. So if I plot out what a band structure for a crystal with this magnetic space group symmetry would look like along the line that connects gamma and z, at the gamma point, all of my states have to come in twofold Kramer's degenerate pairs because of my anti-unitary symmetry. So I'll have a band structure that looks something like this. However many bands I just have a bunch of pairs at gamma. But at the z point, my states are non-degenerate because there is no Kramer's degeneracy. So at the z point, I just have some states. And so what I end up with is this interesting situation where in one plane of the Boron zone at the at k is equals 0 plane, I have twofold degenerate states in my spectrum. And at another plane in the Boron zone, I have one-fold degenerate states in the spectrum. And this is not something that you can ever have in non-magnetic space groups. Okay, so that's pretty much all I wanted to say about little groups and their representations. And now we can move on to try and understand how we can learn about band topology using some of these tools. So before we do that, does anybody have any questions?
Maybe a quick question.
Yes.
So why is the swing matrix for this operation a scalar?
So what I should say is that this is minus the identity matrix.
Okay.
So this here you can think of as the identity matrix, and this is plus the identity matrix. Good, thanks for catching that.
What does one-fold degeneracy mean? No degeneracy?
Sorry, what was the question?
What does one-fold degeneracy mean?
Non-degenerate.
No degeneracy.
Yeah. One-fold degeneracy would be non-degenerate. Yes. Good, thanks for the questions. Okay, so in the remaining lecture and a half, what I want to do is see how we can use these tools to introduce this idea of magnetic band representations and magnetic symmetry indicators. And in a sense, everything I'm going to say will apply for non-magnetic and magnetic groups as well. So I'll try and keep things sufficiently general. So what we've seen so far is how magnetic or Shubnikov space group symmetries can change and constrain band degeneracies in the Boron zone. But we haven't really talked at all about topology. And the way that I want to approach the idea of band topology is to think a little bit about how exactly it is that we end up with band structures in physics. So We know from Bloch's theorem that whenever we have some periodic Hamiltonian, we get a band structure. But when we're talking about solid state materials, we have, maybe a more microscopic picture in mind of where these things come from. We have some atoms. Our atoms have some tightly bound core electrons that we can oftentimes approximate away. They have some valence electrons that contribute to the states that we're usually most interested in for looking at low energy transport properties or optical response. And we put these atoms together. The atoms are arranged in some periodic lattice that is symmetric under one of the magnetic or Shubnikov space group symmetries. And these valence orbitals all hybridize with each other across all of the different atoms. And they hybridize with the core orbitals a little bit, but well, not super important. Usually, even if it is, doesn't really change this picture. What we end up with when we look at what happens after we let these atoms talk to each other is the orbitals hybridize and we end up with some band structure. And running the procedure in this order is sort of what happens when you do a DFT calculation. You specify a structure, turn the crank, and energy bands come out. So schematically, we have some atoms. We put them together in a periodic way, extends in all directions. Turn the crank of solving the Schrödinger equation, and we get some complicated spaghetti of band structure out. But we can try and run this procedure in reverse as well. In particular, we can ask the opposite question of, given our solutions to the Schrödinger equation, can we pick some of them for the bands that we're interested in and Fourier transform them back from momentum space into position space? And can we do this and get a set of functions that approximates our starting orbitals? So what we might want to do is take some set of our Bloch eigenstates, do a Fourier transform, and form a set of functions that I'll call W, that are known as Wannier functions. And what we'd want is these Wannier functions, if we select all of the bands that we get out here, core, all the core states, all the valence states, and all the highly excited states as well, we know that we should be able to reconstruct all of our starting atomic orbitals. But what if we don't look at all of the states? What if we just look at some of them, the ones that we're interested in at low energy? We might still hope to be able to reconstruct some localized functions that respect all of our crystal symmetries and approximate the starting atomic orbitals. In particular, what we want to look for is Wannier functions that are exponentially localized in space, and symmetric under all of the space group symmetries. So what we know is if we have some set of bands here, or let's say we have an insulator. So we have a band structure that looks like the one drawn here. All of these states are occupied, and all of these states are unoccupied. We can ask the following question. let's take the Hamiltonian for our insulator and let's try and adiabatically change it to be the Hamiltonian for a bunch of isolated atoms that aren't talking to each other. One way you could imagine doing that is by taking Hamiltonian that describes your crystal and seeing what happens as you symmetrically rescale all of the lattice directions to move the atoms farther and farther apart. So if we can do this, and if we can do it without closing a gap in the energy spectrum so that our occupied states stay separated from our unoccupied states, what we say is that this insulator can be adiabatically connected to the atomic limit. So an insulator can be adiabatically connected to, I'll say, an atomic limit. If we can symmetrically move all the atoms apart without closing an energy gap. Well, we know that every atomic limit band structure, well, it's made up, the atomic limit is made up of isolated atoms. So we know that such band structure or such an insulator can be described by exponentially localized symmetric Wannier functions. They're just our localized atomic orbitals. And so any band structure that is connected to the atomic limit in this way has exponentially localized and symmetric Wannier functions. And for any such system, we can form these Wannier functions no problem. But we know that there exist insulators that can't be adiabatically connected to an atomic limit. In particular, this is how we define topological insulators. Topological insulators are those that cannot be adiabatically connected to an atomic limit without closing a gap. And what this means is that we can characterize topological insulators in the bulk. Well, if they can't be adiabatically connected to an atomic limit, this means that they don't have symmetric and localized Wannier functions. The advantage to characterizing topological insulators in this way is we can use the tools of, or we can use the space groups and the representations that we've been talking about to come up with a way to characterize these atomic limit band structures. And if we have a way to characterize the atomic limit band structures, we can come up with a set of diagnostic criteria for identifying when the occupied bands of a system cannot be matched by some atomic limit. And this will give us a set of criteria that we can use to classify and characterize, well, classify topological insulators in the magnetic space groups, as well as give some computational tools to identify topological insulators in real material calculations. So our goal, we have two goals. The first thing we're going to do is characterize all atomic limit bands. So those with exponentially localized Bonnier functions, which we'll sometimes call topologically trivial bands. And we'll come up with a way of enumerating all possible topologically trivial bands in a given magnetic space group. From those, we'll be able to identify invariants that tell us when a set of bands is topologically non-trivial. So we'll first do 1, and then we'll move on to 2. So before we get going there, does anybody have any questions about the big picture? Yes.
I have a question related with the shape of the Bonnier function
Mm-hmm.
in the case that we are in the topological insulator material.
Mm-hmm.
There is not a localized Bonnier function. What is the shape then?
Good. So there are two possibilities. Either the Bonnier functions respect the crystal symmetries, but have power law tails, so they decay as 1 over x to some power at large x as opposed to exponentially. Or for certain classes of topological insulators, you can find localized Bonnier functions, but they don't respect the symmetries of the space group. So for instance, if the space group has inversion symmetry, you might be able to find exponentially localized Bonnier functions, but they don't come in inversion-related pairs.
Thanks.
I think the one case where you can sort of by hand do analytic calculations is if you have like a Chern insulator. You can show that the Chern number controls that, or if you have a Chern insulator, your Bonnier functions, instead of decaying exponentially, they decay, I think, if I remember correctly, like 1 over magnitude of r at large distances.
Thanks.
Yep. Yes, question.
In this diabatic transition, are we only concerned about closing the gap or situations like zero crossings or more generally band crossings? Anything to address that?
So as long as the gap doesn't close, so any of these occupied bands can cross with any of the occupied bands. Any of the unoccupied bands can cross with any of the unoccupied bands. We just need to make sure that no gap closes between occupied and unoccupied. Good question. Okay, so let's start by finding a set of criteria that all of these atomic limit or topologically trivial bands need to satisfy. So let's say we pick a Shubnikov space group, I'll call it G. And we want to build a crystal with the symmetries of this space group. So we'll start by drawing some unit cells for the Bravais lattice of this space group. And let's put an atom at some point in one of these unit cells. Let's call that point Q. So we'll put an atom at Q. Now, some of the space group symmetries might leave this point Q invariant. So let's define a group. I'll call it G sub Q. And G sub Q is going to be the set of all of the space group symmetries that leave this point invariant. So a group that leaves a point invariant is called a point group. This is how we characterize our point groups. So G sub Q is isomorphic to one of our magnetic point groups. And it's known as the site symmetry group of Q. And what G of Q tells us is it tells us about the symmetries of the crystal field potential, or the symmetries, the local symmetries of the Hamiltonian evaluated at that point Q. So in order to be symmetric under the space group symmetries, if we have some set of orbitals at this point Q, these orbitals need to transform in some co-representation of G sub Q. So orbitals at Q transform in co-reps of G sub Q. So what this really is this is a group theory way of describing a physical effect that you might be familiar with known as crystal field splitting. So if I have an atom completely isolated in space, everything's rotationally invariant, and I know that my orbitals that solve the Schrödinger equation can be labeled by angular momentum, S, P, D, etc. But when this atom sits inside a crystal, the Schrödinger equation no longer respects all of the rotational symmetries. It only respects the Schrödinger equation at that atom, only respects the symmetries of G sub Q. And so my S, P, and D orbitals split into representations, co-representations of G sub Q. So let's say that we are only considering the valence orbitals of some atom here, and let's say that our valence orbitals, which I'll denote by WN 0, 0. The meaning of those two zeros will become clear soon. Transform in one irreducible co-representation which call a co-irrep. We'll call it rho of GQ. So far, so good. We know at least that the orbitals respect the symmetries of the site symmetry group, which is some subgroup of our space group. But our crystal contains more symmetries than just the site symmetry group. In particular, it has translation symmetry. And so what translation symmetry means, in order to respect translation symmetry, we need to have copies of these orbitals in every unit cell of the crystal. Because I can just take my orbitals at Q and translate them by all of my Bravais lattice vectors. This means that we have copies, which I will denote WN0T, that I get by just taking my original orbitals in my starting unit cell and acting on them with all my Bravais lattice translations. They just translate the functions, and I have to have these. So now I'm part of the way there to building a crystal structure that's invariant under the space group. If I do this, I have a crystal structure that's invariant. This gives me a structure invariant under, well, it's invariant under all of my operations GQ. It's invariant by all of my operations GQ followed by translation by one Bravais lattice vector or by another Bravais lattice vector. And I'll denote this by my whole Bravais lattice T times my whole site symmetry group GQ. This thing is a subgroup of my full Shubnikov space group. And it's actually a symmorphic Shubnikov space group. That's a subgroup of my full symmetry group. It contains all of the rotation and reflection symmetries that leave the point Q invariant and all of my translation symmetries. But I'm still not quite done because my space group may have more symmetries than just these. So I think we're about out of time. So we'll pick up here tomorrow and see what we have to do to finish the story and build a band structure that's invariant under all of my space group symmetries. So I'll stop here for now and take any questions that anyone might have.
I don't see any hands.
Okay. Well, if anyone thinks of more questions in the next hour and a half, I'll be here at the discussion session. So talk to you all then, and thanks for your attention.
Thank you, Larry.
Thanks.
Of half an hour for the breaking.